Hello everyone. Today let us discuss more details about suction stress characteristic curve and how to determine the suction stress characteristic curve, and further to evaluate the effective stress of unsaturated soil from suction control direct shear test data and suction control track shell test data. Suction stress characteristic curve is a characteristic curve represents the variation of suction stress with either matrix suction or normalized volumetric water content. The suction stress consumes energy that is required for the change in the energy of soil water due to several physicochemical factors and capillary effects are consumed into suction stress. So, the suction stress is the suction stress equation, as we have seen, is sigma s dash is equals to, which consists of stresses due to physicochemical forces plus the stresses due to capillary forces plus, so due to the effect of surface tension and this is a cohesion intercept which we use at saturated state. So, this we started writing it as, so this one, the effective stress can be written as sigma dash is equals to sigma minus UA, that is net normal stress, minus sigma S dash. In further works of Liu et al., this suction stress is represented as sigma S as suffix, sigma S in this manner. So, this can be written as sigma minus UA minus sigma S. So, accordingly the sigma S is, the suction stress is equals to minus of UA minus UW if UA minus UW is less than or equal to 0, which means that when the pore water pressure is positive, so negative suction means its a pore water pressure is positive. So, that is normal consolidation test or any other test where the pore water pressures are more than 0, any consolidation or shear strength test where the pore water pressure is positive. So, in that particular case the suction stress is equals to the pore water pressure itself. So, therefore, when you substitute this one here, sigma S here, so this sigma dash becomes sigma minus UA minus UA minus UW. So, therefore, this is equals to sigma minus UW. So, this is the effective stress equation given by Terzaghi itself. So, this boils down to the Terzaghi's effective stress equation. So, this work is from Liu et al. In 2010, sorry. So, in the previous work of Liu and Lykos, they have modified or expanded the Terzaghi's effective stress equation by incorporating physicochemical forces, and if it is unsaturated soil, then all the capillary forces are also included. So, however, in their further work they again approximated their suction stress characteristic curve equation into a simplified manner where this boils down to Terzaghi's effective stress equation for saturated soils. So, for unsaturated soils where UA minus UW is greater than 0, then sigma dash is a function of UA minus UW, this we called suction stress characteristic curve. Sorry, sigma S is function of UA minus UW. So, this is for saturated soils, this is for saturated soils where the pore water pressure is positive, and this is for unsaturated soils where the pore water pressure is negative. So, therefore, the suction is above 0, you have suction in the soil. So, in the Bishop's approach, as we have seen earlier, Bishop in 1950s he has given the effective stress equation, that is sigma dash is equals to sigma minus UA, that is net normal stress plus xi into UA minus UW. So, here he says that xi varies in the same manner as normalized volumetric water content. He often assumes the value of xi to be normalized volumetric water content, or this could be degree of saturation also. So, therefore, comparing this particular expression with this particular expression given by Lu et al., sigma s suction stress becomes simply minus degree of saturation S times UA minus UW. So, therefore, it is an extension of as they are using the degree of saturation here, it is an extension of Bishop's approach and expansion of Terzaghis equation for unsaturated soils. So, therefore, effective stress sigma dash is equals to sigma minus UA minus of minus SC, they have introduced, Lu et al. Introduced a term SC, I will explain what it is, times UA minus UW. So, instead of degree of saturation, if you use SC, which is defined as degree of saturation at any given water content minus degree of saturation divided by 1 minus SR. So, this is defined in this particular manner, C is equals to S minus SR by 1 minus SR. So, this is equals to sigma minus UA minus, so minus of minus So, this is same as Bishop's expression, except that they have used normalized degree of saturation here. So, for saturated soils SC is equals to 1 for saturated soils, S equals to 1 which boils down to Terzaghis one dimensional consolidation equation, sorry Terzaghis effective stress equation, and when S equals to 0, this is a dry condition, which is sigma dash is equals to sigma minus UA. So, that is equivalent to the Bishop's expression for dry soils. So, here the additional advantage they have given is that they assume that SC is a function of matrix suction, and which assumes a form of Van Jenissen equation. So, the Van Jenissen equation, which can be written as 1 over 1 plus alpha times UA minus UW whole power n whole power m, but they assume m to be dependent on n. So, this is 1 minus 1 by n. So, this is the form they assume to be existing between SC and UA minus UW. So, this SC could be normalized volumetric water content also, that is big theta, which is theta minus theta s, sorry theta r by theta s minus theta r, which is similar to this. So, you can assume normalized volumetric water content also instead of SC. So, they assume this form to be existing, then the sigma s can be simplified as minus UA minus UW minus UA minus UW divided by 1 plus alpha UA minus UW whole power n whole to the power of n minus 1 by n. Expression for suction stress, and as a continuous form it can be defined suction stress characteristic curve. The dependency of suction stress on matrix suction can be defined in a continuous manner using this expression. So, this is one expression, and other expression is in terms of SC. So, SC here UA minus UW can be written as SC power n by n minus 1 and minus 1 whole power 1 by n 1 by alpha. So, this is UA minus UW. So, when you write UA minus UW in terms of SC, this is what you get, and when you substitute this in the suction stress characteristic of equation, so we get minus SC by alpha SC power n by 1 minus n, and minus is taken in here, this becomes 1 minus n minus 1 whole power 1 by n, where SC varies between 0 and 1. So, this is another expression in terms of SC. So, if soil water characteristic curve data for any given soil is known under any given stress state, either applied mechanical stress or something, so then the suction stress characteristic curve or the effective stress of the soil can be determined by simply substituting these parameters. Here alpha is the bubbling pressure or is related to bubbling pressure or air entry value AEV, and N is pore size distribution factor. So, essentially the SWCC of the soil can be directly utilized to determine the soil suction stress characteristic curve. So, from that we can obtain the effective stress of the soil. So, this is very useful. So, then you can obtain the effective stress by simply summing up sigma minus UA minus sigma S, anyway minus n you have there. So, this is simply plus UA minus UW divided by 1 plus alpha UA minus UW whole power n minus 1 by n. So, here UA minus UW is greater than or equal to 0. So, sigma dash, this is the effective stress equation. So, for several soils, when the SC versus UA minus UW is plotted, so this can be plotted as like this for goes to 0, this is for clay soils, this is for silt, this may be for sand. The suction stress characteristic curve can be drawn UA minus UW and SC for clay soils. So, this is how the SSCC varies for clay soils. For silt soils, as we have seen yesterday, the suction stress characteristic curve decreases and goes to 0. Sorry, this is sigma s in negative kilopascal. Then for sandy soils, this goes somewhat like this. The suction stress characteristic curve increases and nearly become constant and then goes to 0, because the capillary effects are dominant only at some particular value, and beyond that, that is after the air entry value, the capillary effects are predominant, and beyond that again as the degree of saturation goes to 0, approaches 0, the capillary effects are absent and suction stress approaches 0 for sand soils and silts. Similarly, if this is plotted in terms of U minus UW and sigma s, so sigma s, that is suction stress on y axis and UA minus UW on x axis. So suction stress increases and becomes nearly constant for clay soils, and which increases and decreases beyond certain suction value for silt soils. For sandy soils, this increases and decreases and goes to 0 at higher suction values. So this is how the suction stress characteristic curve varies for different soils. These are the solutions. This is the data obtained from closed form solutions for different, by assuming different values of alpha and n. Here the clay soil has very high value of air entry value, so alpha is accordingly adjusted and some n value is assumed, and similarly silt value, the alpha value slightly got changed because the air entry is slightly smaller, and sand, the air entry is smaller. So that is how these three curves are generated on SWCC using Van Jenichen equation in using m and n dependent equation. So once this is derived and the SC versus sigma s is directly obtained by substituting these values into this equation, and for any given SC, which SC changes from 0 to 1. So knowing the alpha and then n parameters from SWCC equation, for clay, sand, silt and sand, these parameters are substituted and then sigma s is plotted in this manner. Similarly, this third figure, sigma s versus U minus UW is obtained using this particular equation by again substituting alpha and n parameters into this equation, and U minus UW is varied over a wide suction range, and then sigma s is plotted in this manner. So they have proposed two approaches for estimating the suction stress characteristic curve. One is a semi-quantitative approach, so the Liu et al. In 2010, they have come up with two approaches. Semi-quantitative approach, this approach is used when soil water characteristic curve data is not known. Only the shear strength data from suction control direct shear tests and suction control triaxial tests are known, then this particular approach could be used to derive the effective stress variation within the soil mass, the suction stress variation with either suction or volumetric water content. So for the direct shear testing, the Moore Coulomb failure criterion is tau f equals to, this is for direct shear, tau f equals to C dash plus sigma minus UA plus minus sigma s tan phi dash, because the effective stress is sigma minus UA minus sigma S. So, this is the effective stress. The total stress or net normal stress minus the suction stress is the effective stress. So, the Moore-Coulomb failure criterion is tau f equals to C dash plus sigma dash tan phi. When sigma dash is substituted here, then this is the equation. So, therefore, the suction stress can be obtained by for any given matrix suction. At any given matrix suction, the suction stress is sigma S is equals to minus tau f minus C dash minus sigma minus UA at failure tan phi dash by tan phi dash. So, this equation can be used for determining the suction stress characteristic curve if the soil water characteristic curve is not known. So, let us solve an example problem. When the suction control direct shear, when the shear test data from suction control direct shear tests are obtained on some silty soil, this is a generated synthetic data. So, number of tests performed and the suction value controlled, sigma minus UA at failure, that is net normal stress which can be controlled, and tau f which is measured. So, here the first number of tests are 9. Two tests are conducted at saturated condition. So, suction varied in this manner in these tests. So, the net normal stress varied in the first two tests, which are saturated tests, so that different shear strength will be obtained. So, from that the strength parameters of saturated soils can be obtained. For remaining tests, the net normal stress is maintained constant, only the matrix suction is varied. So, this test data is used, this test data were used earlier for demonstrating the Bishop's approach for the prediction of Xi-F calculation. So, same test data is used here. So, here, so for saturated tests, when soil is saturated, for saturated condition, so tau f equals to C dash plus, so this is simply sigma dash, or you can write sigma minus UA, and suction stress is 0 anyways, tan phi dash. So, therefore, solving these two equations, 294 is equals to C dash plus 300 tan phi dash, and 136 is equals to C dash plus 120 tan phi dash. Solving these two, we get phi dash is equals to 41.3 degrees and C dash is equal to 30.4 kilopascal. So, knowing these two shear strength parameters, so the effective stress parameters, so shear strength drain parameters phi dash and C dash, so we can obtain the suction stress at any given matrix suction value. So, the sigma s is equals to minus, here if you are giving the suction stress characteristic suction stress values. So, this is 0 here and 0 here, and for the third data test 3, suction stress is minus tau f is 156 minus C dash is 30.4 minus sigma UA is 120 tan 41.3 divided by tan 41.3. So, this value comes out to be minus 22.97 kilopascal. So, we can substitute the data for all the values, minus 22.97, and for this is minus 41.18, and this is for minus 50.29, minus 55.97, minus 59.4, minus 61.67, minus 55.98. So, these are the suction stress values, and we can also compute for comparison xi f, because this equation is quite similar to the Bishop's equation. So, the Bishop's equation, if you compare, that is sigma minus UA plus xi f UA minus UW. If you compare these two equations, sigma s is nothing but minus xi f UA minus UW. So, therefore, xi f is equals to minus sigma s by UA minus UW. So, here UA minus UW is 0, xi f is nothing but 1, this is maximum value is 1. So, this is 1, and here this is minus 22.97 divided by minus 25, this is 0.918, and similarly if you get all the values 0.824 and 0.503 and 0.28, 0.148, 0.123 and 0.075. So, this is the xi f data, and in fact, if you compare our earlier calculations where we estimated the Bishop's effective stress parameter using the same data, and if you compare, the xi f data is same. So, therefore, it is not a big modification we have done here using suction stress characteristic curve, only the representation of effective stress is more effective here in this case. Similarly, in the semi-quantitative approach for triaxial testing, if you have a data from suction control triaxial tests, then sigma s can be represented as minus sigma 1 minus UA at failure minus sigma 3 minus UA at failure tan square 45 plus 5 by 2 minus 2c dash tan 45 plus 5 dash by 2 divided by 2 tan 45 plus 5 dash by 2 times tan 5 dash. So, this is a expression can be used to determine the suction stress if the major principal stress at failure and minor principal stress at failure are the net normal stress in the vertical direction and net normal stress in the horizontal direction, or radial directions are known at failure, and we can determine the suction stress. So, let us solve another example for this. So, the test data so here also we utilize 9 test data. So, this is metric suction in kilopascal. This is varied in this manner 0, 10, 25, 50, 100, 200, 400, 500, 750. So, as the metric suction is only the saturated state, at the saturated state only one test are conducted. So, therefore, this must be for sand, for sandy soil, and sigma 1 minus UA at failure, this is 180, these are observed data. So, sigma 3 is maintained constant. So, we can obtain the sigma s, we can calculate the xif, and we can also estimate the phi b, so that we can compare Bishop's approach and Friedland's approach with SSCC. So, now using the first test data, either to obtain the angle of interflexion, either you can use this equation. So, here anyway C is 0 because it is sand. You can directly use this expression, or you can use sin phi dash is sigma 1 minus UA at failure minus sigma 3 minus UA at failure by sigma 1 minus UA at failure plus sigma 3 minus UA at failure because when you are plotting tau versus sigma, and if this is a failure envelope and this is more circular and this is a failure envelope, and this is angle of internal friction phi dash, and if you take sine, so this is sigma 1 minus, this quantity is sigma 1 minus UA minus sigma 3 minus UA whole divided by 2, when this is a major principal stress at failure and this is minor principal stress, and this quantity is equal to sigma 1 minus UA plus sigma 3 minus UA by 2. So, if you take sine, then this side divided by this one, so you get this expression. So, if you use this expression 180 minus 50 by 180 minus 50 by 200 minus 50, sorry, 180 plus 50 from the first expression. So, you get phi dash, which is equals to 34.42 degrees. Once phi dash is obtained, you can calculate sigma s. Suction stress is equals to minus sigma minus UA is sigma 1 minus UA is 200 minus sigma 3 minus UA is 50, tan square 45 plus 34.42 by 2, and anyways 2c, this is whole thing is cancelled for sand, and divided by 2 tan 45 plus 34.42 by 2 times tan 34.42. So, if you solve this, you get a value of minus 7.68 kilopascal. So, there is a suction stress. So, suction stress minus 7.68 kilopascal. So, the first value, this is 0. So, similarly, if you get all the other values, this is minus 15.37, this is minus 19.22, and this is minus 23.07, this is minus 26.91, this is minus 32.68, this is minus 38.45, minus 46.14. So, the xif can be obtained in the same manner, which is nothing but minus sigma s by UA minus UW. For the first data, for saturated state, xif is 1. For other values, this is 7.68 by 10, therefore 0.77, this is 0.615, this is 0.3844, this is 0.231, 0.135, 0.0818, 0.077, 0.0676. You can obtain phi b also. Phi b is tan inverse of xif tan phi dash. So, that is because the Fredland et al. Expression for the strength envelope is tau f equals to sigma minus UA plus tau f equals to C dash plus sigma minus UA f tan phi dash plus UA minus UW F times tan phi b. If you compare this expression and the Bishop's approach, tau equals to C dash plus sigma minus UA tan phi dash plus xi f tan phi dash tan into UA minus UW. If you compare these two expressions, xi f tan phi dash is equals to tan phi b. So, phi b is nothing but tan inverse of xi f tan phi dash. So, this is what is utilized here. So, after utilizing this, we can write the phi b values. So, phi b values varied in this manner: 34.42, 27.82. So, the phi b is decreasing as the suction is increasing. 22.85, 14.76, 8.995, 5.29, 3.208, 3.02 and 2.65. So, phi b continuously decreased. So, we can see the variation. We can see the variation if the suction stress is plotted sigma s negative kilopascal with respect to U minus UW. We see that when this is varying between 0 and 50, and if the suction is varying between 0 and 800, because the suction maximum value is 750. So, if the range is this much, then this varies in this particular manner. So, this is a typical SSCC curve for the given data, and if the xi f is plotted for the same variation of U minus UW, xi f varies from 0 to 1, and this is 0 to 800, and this decreases in this manner. It approaches to 0 somewhere. So, this is Bishop's approach. This is Liu et al. Or Liu and Lycos, and this is Bishop, and you have Friedland and Morgenstern or Friedland et al., where U minus UW variation with phi b, and here it is 0 to 800, and this is 0 to 35 maximum angle, which is equals to nearly phi dash. So, then this also decreases in this manner. So, this is Friedland et al. Or Friedland Morgenstern. So, even though there are different expressions and different researchers have attempted to understand the effective stress of unsaturated soils, so essentially there are different parameters in each model, either suction stress or xi f effective stress parameter or phi b. So, these values vary in the same manner and the approaches are nearly same, except there are minor variations. So, because of this, the representation becomes different from each model. So, in the first representation, that is Liu et al., we determine the suction stress, and by adding the suction stress to the net normal stress, this becomes effective stress. And in the other approach, we determine the xi f suction effective stress parameter. So, the effective stress parameter indicates the contribution of suction to the shear strength of the soil. And Friedland and Morgenstern and Friedland et al., they have proposed a similar approach where phi b is considered. So, this because of this representation of failure envelope using tan phi b. So, the representation of failure surface is very clear and easy to understand. However, because the phi b itself varies with suction, this adds more difficulties in determining the phi b. We require huge data sets to determine the phi b parameter, similar to xi f and similar to any other, similar to even suction stress. So, if the soil water characteristic of data is not known, so this phi b variation, that is decreasing with increasing suction, is similar to tau f versus u minus uw variation. So, for a given net normal stress, the tau f may increase and becomes nearly constant and starts decreasing. This is the observations from experiments. This decreases like this. So, this itself is phi b. Phi b increases at the nearly same angle as phi dash, but later on it starts decreasing and nearly becomes 0. Phi b is 0 here, and even it decreases, negative value it approaches, it gives a negative value too. So, that is observation, that is what is indicated here. Phi b is plotted with respect to suction, that is what is indicative. Liu et al. Further came up with quantitative approach. Where the SC is determined and which is assumed to be related to psi or matrix suction as determined using Van Junichen expression, and then sigma s is determined. This quantitative approach is useful. Okay. Sigma s is equals to minus SE by alpha SE times n by 1 minus n minus 1 whole power 1 by n. SC varies between S0 and 1. So, then sigma dash that is effective stress is determined in this manner. In the absence of any external stress on soil specimen during SWCC tests, so this is absent, so therefore sigma dash is equal to minus sigma s itself. In the absence of external stress during SWCC determination. So, effective stress is directly equal to the minus suction stress. So, this approach is proposed when soil water characteristic curve data is known. So, then the soil water characteristic curve data can be fitted with Van Junichen model with m and n parameters related, and using alpha and n we can determine the suction stress and the effective stress can be determined. So, this is how the suction stress characteristic are determined and effective stress of the soil in unsaturated state are determined. So, this is a completion of shear strength topic, and I will summarize what we have learned so far. In the beginning, historical developments we have seen where the Coulomb in 18th century proposed the shear strength model, that is tau equals to sigma tan phi. So, the total stress controls the shear strength of the soil. That is his approach, where he proposed a one phase model, such as he considers soil as nothing but a weak rock mass. So he does not distinguish between soil and rock, only the difference between these two is the strength of the material changes from rock to soil. So he proposes that the shear strength varies with sigma, the total stress or the total stress. So therefore the direct shear tests were obtained, direct shear tests were designed, and the tau versus sigma plots could be obtained by conducting several tests by varying the net normal stress on the soil, normal stress on the soil. So the shear stress and shear strain profiles are obtained for heavily compacted sand and loosely compacted sands. So this is a critical stage, and this is a critical shear, and this is a peak shear. So this is at one net normal stress. This is at one normal stress. So if this is plotted with normal stress, so then you get the data. If you fit with a straight line, fit with a linear line, you get angle of internal friction phi dash, and you get an angle of internal friction phi dash. So therefore the shear strength of the soil can be determined using the shear strength is assumed to be dependent on directly total stress. So the angle of internal friction of the soil can be determined directly. So here it should be used phi, there is no phi dash when this was proposed. Then later in Terzaghi in 1920 came up with effective stress principle, that is sigma dash should be equals to sigma minus UW. So here mostly the stress is on two phase system, soil solids and water. He considers soil solids and water, and if you have a two phase system, the sigma dash effective stress is equal to sigma minus UW. So then the importance of pore water pressure in the determination of shear strength of the soil came into picture, and the triaxial tests were designed to control the drainage. Then by controlling the drainage valve, drained and undrained tests are conducted, and in the drain tests essentially you get same size the Mohr circles. Essentially when the sigma 3 is maintained particular value and sigma 1 is varied, and the soil fails in this manner. So these are undrained tests, and if the sigma 3 is increased and the radius of the Mohr circle does not change, and this is another F. So essentially you get shear strength of the soil in an undrained manner. The undrained shear strength of the soil are obtained, so which are used for short term analysis. So if in the same test, if the pore water pressure is measured at the failure, so then pore water pressure is measured, then effective stress envelopes also can be obtained, and all these things will merge into one single Mohr circle. Then you get effective stress parameters. So you can determine effective stress parameter, and then you can determine the drained parameters and undrained parameters in the same test called consolidated undrained test. Similarly, the drain test can be conducted where tau f and sigma dash variation can be obtained. So for clay soils, there is an intercept which is seen, which is equal to tensile stresses. So and this is the intercept, and this is angle of internal friction. So using C dash and phi dash, the equation is modified now as C dash plus sigma dash tan phi dash. So C dash and phi dash are the shear strength parameters. Shear strength parameters are material constants, and sigma dash is effective stress. And Bishop later on in 1950s came up with two stress state parameters or two stress state variables for understanding the shear strength of unsaturated soils. So, here sigma dash plus sigma minus UA plus xif UA minus UW. So, the xif is the effective stress parameter which indicates what is the contribution of UA minus UW on the effect on the shear stress or shear strength of the soil. So, there were several tests conducted by controlling the suction in the direct shear tests and triaxial tests, where the data obtained in this particular manner, sigma minus UA. If the tau and sigma minus UA is plotted for saturated state, so this is the failure envelope obtained, this is with phi dash, and this is for UA minus UW is 0, and this is for another. Similarly, for other envelopes for different UA minus UW, say 50 kilopascal, and this is for another UA minus UW. Angle of internal friction nearly constant, hardly varies within 4 to 5 degrees. Similarly, the tau by sigma minus UA, if it is plotted with shear strain, so this is how the stress strain curves varied for different matrix suction values. So, therefore, these can be analyzed using Bishop's effective stress principle, extended effective stress principle. This data can be very well be analyzed by determining xif parameter, for direct shear, and similarly for triaxial tests we have seen how to determine. Here for different UA minus UW values, initially the tests are conducted at completely saturated state, and then C dash and phi dash are obtained. Then when the UA minus UWs are varied, the xif parameters are obtained. Then xif relationship with UA minus UW are obtained. This relationship is used to define the stress state of the soil very accurately